let's continue our discussion of solutions and how they form. And we're going to do that here by just talking about some general facts and general terms that we use when we're talking about solutions and if one thing will dissolve in something else. So we're going to be talking about solubility here specifically, and what the solubility is, what that's referring to, is it's the maximum amount of solute that can be dissolved in a given amount of solvent. That is the solubility of that molecule. So when we talk about making solutions and we talk about one thing being dissolved in something else, that is not, for some things anyway, that is not going to infinitely dissolve. One molecule is not going to infinitely dissolve in another molecule for some things. And so for those materials where there is a limit to how much one thing can dissolve in something else, we call that the solubility of that molecule. And usually when we do this, we're going to be talking about a solid dissolved in a liquid. There are other times where something is going to be infinitely miscible, is what we would call it, to where there is no limit to how much one thing will dissolve in something else. This is usually true for one liquid in another liquid. Not always, but usually. It is always true for gases. There is no limit to how much of a gas will dissolve in another gas. Gases are always completely soluble in one another. And some liquids are as well, like I said. So for example, alcohol and water. Those are going to mix. They will form a solution no matter how much of one or the other you have in your sample. They're always going to mix together. Oil and water, on the other hand, there is no amount of one or the other that will dissolve at all. So you kind of have the opposite there. Oil and water will not dissolve no matter what the amount of one or the other is. Alcohol and water will always dissolve no matter what the amount of one or the other is. And this will also change with temperature, as we'll see later in later slides. So our general rule of thumb when it comes to solubility and if something will form a solution with something else is like dissolves like. And what that's saying is that if you have two molecules that are similar in terms of their intermolecular forces specifically, so if two molecules have similar intermolecular forces, they will most likely form a solution. Now again, there's exceptions to practically everything, but we are going to just look at the ones that follow the rules here. So if you have, for example, two polar molecules, those will form a solution. Now we don't know how much will be soluble, but we know at least will form, it'll be somewhat soluble. It could be very soluble, where a lot of it will dissolve, or it could be slightly soluble, it just depends. But it will form a solution if they are both polar. And ionic compounds, by the way, are essentially just a souped-up version of polar molecules. If you remember from the last chapter, polar molecules have a very slight charge. Ionic molecules have, or ionic compounds, I should say, have a whole charge. So they very much like each other. This is why salts usually dissolve in water very well. But if you have a polar molecule and a nonpolar molecule, those will not be soluble. They will not dissolve in one another because they are dissimilar. And it's not because the two dislike each other. It's not that the polar molecule is like, ew, look at those nonpolar molecules over there, gross. It's nothing like that. It's just that the polar molecules really like each other, and the nonpolar molecules like each other as well. So essentially, once again, they're with their buddies, and it's not that they dislike the other molecules. It's just like, well, why would I want to go over and be dissolved in there when I have much stronger interactions with my friends over here? And so it's not that they dislike each other, it's just they much prefer to be with molecules that have similar intermolecular forces. All right, and so we can see that here in this table where we look at a series of alcohol molecules. So we have the OH group on each of these is going to give the molecules a certain amount of polar nature. But as we go down the table here, we are increasing the amount of the nonpolar nature. As you can see here that we're adding on a CH3 every time, essentially, or really we're adding in a CH2, actually. So we're adding in a CH2 with each molecule, and carbon-hydrogen bonds are not polar, so we're increasing the nonpolar nature of the molecule. And as we go down, we can see that these first three molecules are infinitely miscible in water, so any amount of these will dissolve in water. But then once we get to butanol and pentanol, yes, they are still soluble. There's some amount of it that will dissolve in water, but it is limited now, especially with the pentanol. It's not very much. You can't get very much pentanol to dissolve in water. On the other hand, if you look at the solubility in hexane, which is very nonpolar, methanol is only slightly soluble in that, and all the rest are infinitely soluble. They are miscible in hexane. So this one, just because the nonpolar and the polar portions of the molecule are roughly the same size, it's not terribly soluble in the hexane. But then once you get even just a little bit more of that nonpolar section of the molecule, now it will dissolve in hexane completely. Alright, so let's talk about enthalpy and the energetics of things dissolving. So when we're taking a molecule and we're dissolving one molecule in another molecule, there are certain steps that have to be taken. We can essentially break the process down into 3 different steps. So the first step that has to happen is that we have to take the solute particles and break them apart from each other. Because if you remember, the solute particles are attracted to each other. They have intermolecular forces that are holding them together, and we need to break those so that it will dissolve into the solution. So we break that apart. To do that, we have to put energy in. So we have to put energy into the system to overcome those interactions. You could think about it in terms of like, I don't know if you ever played the game Red Rover, but in Red Rover you have the kids and they're holding hands as tight as they can, and somebody tries to break the link between the two kids, and you have to have a certain amount of energy to break that link between them. You have to put energy in to cause those to break apart. It's kind of the same thing, where these molecules are held together by these intermolecular forces, and you have to put energy in to break those. The same thing is true for the solvent. You have to put energy in to break apart the solvent molecules so that there's space for the solute molecules to go in there and be dissolved. So both of these first 2 steps are endothermic because we have to put energy in to get them to happen. They have to suck energy from the surroundings, which makes it endothermic. And then the third step is forming new attractions between the solute and the solvents. So once we've broken the 2 apart, we stick the 2 together, and they realize, oh, maybe there are some new nice interactions, new intermolecular forces for me to participate in here. And so we get some of that energy back because they go down to lower energy as they form these new favorable interactions. And so this is an exothermic process. And so then all 3 of these put together gives us what we call the heat of solution. So these 3 steps, we're pretending like they happen separately, but in reality they're all mixed in together. They're all occurring simultaneously. And so the 3 of these added together gives us the enthalpy change for the overall process. And so we have 2 different options for when this happens. And by the way, this is just kind of graphically showing you what I was just talking about. Separate the solute, separate the solvent, put the two together, and you make a solution. And so we have two different possibilities for the end result of these mixing processes. One possibility is that the two processes where we have to put energy in, breaking apart the solute, breaking apart the solvent, it has a certain amount of energy here that it takes to do that. It takes this much energy. If we're saying energy here, if energy is the this axis, and so as we go up, we're at a higher energy. So there's a certain amount of energy that it takes to do that, because this is our starting point here. And so if we go up from here to separate them, and then when we put them back together, if we get more energy back than we had to put in to break them apart, then overall the process goes down in energy, which will be a net release of energy, which is an exothermic process. So this would be a hot mixing process. Remember, exothermic processes feel hot to us because heat is released to the surroundings, and we are part of the surroundings. And so heat is released to us, and so it feels hot. This is what happens anytime you mix acids and water, by the way. This is why they always say that you should add acid to water, not the other way around, because if you add water to acid, you can actually flash boil the water because of the amount of heat that's released. And so you would rather add acid to the water, because then you have essentially the heat sink of the water that's able to, or of the the large amount of water, so that it doesn't boil over as easily. But anyway, so that is one of the possibilities, is an exothermic mixing process. But it's also possible that these first two steps actually require more energy than you get back. So maybe breaking apart the solute is actually really difficult. Maybe there's really strong intermolecular forces between the solute molecules. And so overall, when you go and mix them together with the solvent, you don't get quite as much back as you had to put in. This would be a net endothermic process. And these do happen, even though enthalpy does not favor this. So enthalpy does not like this mixing process. Enthalpy always wants to go to a lower energy. But remember, enthalpy is not the only thing that gets a say here. Entropy also gets a say in what happens. And so these processes where you have a net endothermic mixing, it's because excuse me, it's because entropy really wants that mixing to happen. And so it essentially overrides the enthalpy and is able to cause the mixing to occur. So this type of mixing process would be cold to us. By the way, this is the type of process that happens in chemical cold packs, ice packs. So if you've ever played sports and you got a sprain or something, and they took one of those packs and they broke the water pouch inside, and it got really, really cold really fast, that was because of an endothermic mixing process. There was a, I want to say it's ammonium nitrate that's in there, and it mixes with water, and that is a very, very cold mixing process. Alright, I think we'll call it there for this video. It's kind of a longer one, but hopefully you managed to get through there okay. In the next one, we'll talk a little bit more about solubility and kind of breaking the rules even with solubility, talking about supersaturated solutions. So I'll see you in the next video.